Welcome. In this video, we'll take a look at how the NES represents images. We'll find out how this turns into this. And for those with no experience with computer graphics, I'll also include a brief primer. This video is part of a series on the NES, but this video stands on its own. If you'd like to learn more about the NES, I'll leave a link to the first video in the description. Now let's start with computer graphics. We know that computers represent everything as numbers. Images are no different. There are two main styles of representing graphics. There are raster and vector images. Raster images are built out of dots, and vector images are built out of lines. Most 2D graphics systems use raster graphics, so that's what we'll look at here. A raster computer image is a collection of pixels, which is actually short for picture elements. Each of these pixels is a single dot and has a color. An image is a grid of pixels, and when these pixels are all placed together, it looks like an image. One way of representing colors is by mixing different amounts of red, green, and blue. The color depth is a term that we'll sometimes see applied. This refers to how many different possibilities there are for each of these color components. For example, 1 byte is used for each of the red, green, and blue components. Since each byte is 8 bits, this turns into a 24-bit color depth and allows 256 possibilities for each of the components. So 256 cubed is quite a large number, which is often summarized as about 16 million colors. Here we'll take a look at a color picker, which lets you see the various colors and their representations in different ways. The RGB number we have at the bottom here corresponds with this representation we were just talking about. And since only 1 byte is used for each component, 0 is the smallest value, which means none of that color, and 255 is the max. And with that, we have enough knowledge about computer graphics to jump into understanding how the NES represents image data. For the rest of the video, I'll be using examples from the nestest test ROM. In the previous videos, we've been using it without graphics, but if you actually run it on a system with graphics support, it has a very simple menu that looks something like this. Now we can start taking a look at the character ROM, which is what holds all the image data on the cartridge. Just like when we were looking at the INES header, we'll understand this by taking a look at the hex dump. First, we need to find out where in this dump the character ROM starts. We know that the layout of the entire file looks like header followed by the program ROM followed by the character ROM. We've already looked at the header and program ROM previously, and we know that for this file we have a 16-byte header and the program ROM is 16,384 bytes. So if we add these together and then represent it in hex, 0x4010 should be where the character ROM starts. So here we can see the first byte of character ROM. Unfortunately, we can see the first many bytes are all zeros. This won't be very interesting to look at, so let's try to skip ahead a little bit. Each of the positions in the character ROM can be interpreted according to this little layout. Here we have each of the bits numbered and sort of a name applied to the significance of each of these bits. Here we can see all the way on the right the least significant bits, which we can think about as being the things that come first in the file, correspond with the row, or Y. The character ROM data represents images as tiles. Since the 4 least significant, which are the bits closest to position 0 all the way on the right, are used within a tile, we will have from 0 up to binary 1111 before reaching the next tile. So this tells us that each tile starts on a multiple of 10000, or 16 bytes. So we're going to skip ahead some multiple of 16 bytes to find a tile that isn't all 0. We'll actually skip ahead by 16 times 3, or 48 tiles. And taking this 48 times 16 bytes per tile in hex is 0x300 bytes. So adding this to the start of the character ROM, we will look at hex 4310. Let's see. Now we have quite a bit of data, and none of this looks like zeros. Now that we've found the data, let's go ahead and try to decode this by hand. Now, the way this is represented, the character ROM has 2 bits per pixel, and these bits are not next to each other, but are instead split up into what are called planes. For a single tile and a single pixel, all of the bits in the zeros place, or bit position 0, come first. And then we have kind of another copy of the image, but now it's all the 1 position bits. The NES is responsible for putting these together whenever it needs to read an image. We'll walk through an example to make this more clear. So to decode one tile starting at position hex 4310, we need all the rows for plane 0 and all the rows for plane 1. We know it's 16 bytes for an entire tile. Split into 2 planes, we'll have 8 bytes per plane. So the first 8 bytes are for plane 0, and the next 8 bytes are for plane 1. So we can go ahead and highlight to see what these are. I'll just go ahead and copy down the bytes from plane 0 and the bytes from plane 1. Fortunately, this makes things a little easier in that the 2 planes hold exactly the same data. So we can just go ahead and decode one of the planes by hand and know that the data held in the other one is the same. Tile data represents an 8x8 image. Each byte represents 1 row, and each bit within that byte represents a single dot from left to right. So in order to make sense of this image, it will be helpful to look at the binary representation of each of these numbers. I'll go ahead and do that here. And the numbers are arranged from top to bottom because each of these correspond to 1 row. And if you squint just right, you might actually be able to see the image here. But in order to make it even more clear, what I'll do is take all the zeros and just replace them with spaces. And my font on screen is what is called monospaced, so all the characters are the same width, which makes it easier to see things arranged in a grid. And with that we have, pretty cool, huh? Let's go ahead and decode the next tile as well. So copying the relevant bytes, again we see planes 0 and 1 have the same data. Here are the binary representations, and then we clean it up and we have, great. Now that we have decoded 2 tiles and can visually see the pattern, let's talk a little more about what this is actually doing. We mentioned earlier that each pixel in a tile is represented by a 2-bit number, and these bits come from plane 0 and plane 1. Since the 2 tiles we looked at were the same in these 2 planes, that means that every value from these tiles is either representing binary 00 or binary 11. It's hard to represent much information at all with only 2 bits, because we only have 4 possibilities here. So rather than pointing to a color directly, these numbers actually refer to positions into something that is called a palette. Something that you'll see both in my debugger and several other popular emulators is the idea of using grayscale to represent the tile data. Gray is nice because it kind of indicates that the information here doesn't have a color. And by using different shades of gray, it makes it possible to see and recognize patterns in this data. Here's how we could represent the 4 possible values with the grayscale palette that I just mentioned. Again, we'll cover palettes next time, but this just helps illustrate for the time being. So 00 represents the darkest color, and 11 represents the brightest. I mentioned that I'm working on a debugger for the NES as well as an emulator, and my debugger makes it possible to visualize the character data using this grayscale palette. I will include a link in the description. If we use it to visualize the entire character ROM, it ends up looking like this. One detail we haven't mentioned yet is that the NES treats the character ROM as 2 tables of tiles. It is often the case that one side is used for background images and the other is used for characters or things that move around. For the ROM that we're looking at, nestest, it only needs to draw text, and there really aren't even that many characters. So we can see that only one of the tables is used, and it's only about halfway full. Now, at this point, you might be wondering why the image data is organized this way. Splitting into 2 separate planes makes decoding a bit simpler, and this decoding was done with hardware and not software, so simplicity also helps save money. As for why only 2 bits per pixel are used, this is a space-saving optimization, which helped reduce the cost of storage needed. Every single cartridge would need to have a character ROM chip. The nestest ROM has an 8K character ROM chip and is storing 2 tables, each 16 by 16 tiles, and each of these tiles 8 by 8 pixels. If we were to instead represent this data with a modern image format, each pixel would be 3 bytes. This would then take 2 times 16 times 16 times 8 times 8 times 3 bytes to store all of the character ROM data. This turns into about 98,000 bytes. This is more than 10 times what was actually used in the NES. And when you consider that the ROM chips were a significant portion of the cost, I think few people would have been happy spending 10 times as much for a game cartridge. The other nice thing about using positions into a palette is that it makes possible certain types of animation that would be impossible or at the very least challenging with the limitations of this system. And with that, we know all there is to know about how images are stored on the NES. But this graphic data wouldn't be much fun without color, and so that is what we will be looking at next. Hope you enjoyed the video. If you did, consider liking and subscribing, and hope to see you on the next one.